Okay, welcome to week 2, lecture number 1. I'd like to start by reviewing what we did last week. So in the first lecture, we took a look at some Python basics. We talked about the shell, comments and variable names, arithmetic operators, in which multiplication and division have higher precedence than addition and subtraction, as one might expect. We used a combination of meaningful variable names and arithmetic to do things like Fahrenheit to Celsius temperature conversions. We introduced the exponentiation operator, which has higher precedence than all of the other arithmetic operators. We took a look at the unary minus and the unary plus, the latter of which you'll never see except for this example in the course. And we looked at modulus for computing remainder after division, and floor division for computing the quotient of division. So here on slide 20 is the complete table of these arithmetic operators ranked from high precedence to low precedence. And then finally we introduced the int and float data types. The int data type is arbitrary precision. You can have enormous integers, both positive and negative. The float data type, on the other hand, is more restrictive and has to fit within a 64-bit representation. Okay, so that's the key things from the first lecture. Then in the second lecture, we introduced some other low-level so-called scalar data types, namely the string, Boolean, and the special value none. We saw examples of strings using single quotes, double quotes, triple single quotes, and triple double quotes. We talked about writing code in a code file using an integrated development environment, such as the idle editor. And we described that if you put code in a file, you're going to need to use the print function in order to be able to display values. And so here is another example of our Fahrenheit to Celsius conversion computation. In addition to taking so-called positional arguments that are simply processed from left to right, many functions also accept what are called keyword arguments, where you provide the name of the argument and an equal sign and then the value that you want that keyword argument to have. So in this case, we saw that we could change the default separation between values that print displays from a space character to a comma character. We introduced the list data type, which is a collection of values. You can define a list by putting a sequence of values into square brackets. You can then index individual items within the list. You can use plus to concatenate two lists, or times to perform a repetition of some list. And we saw that there were several named methods that you could use to interact with lists. A list is an example of an iterable, and we introduced the idea of a for loop that you can use to step through each of the items in an iterable. Here on slide 27, we had an example of stepping through each of the items of a list. It turns out that a string, a str, is also iterable. And so we used a for loop to step through the items, that is, the one-character substrings of a string. And finally, we introduced the range function, which is yet another kind of iterable that allows you to step through a sequence of integer values. And we saw that by using appropriate arguments, you can use a range to step up through a sequence or to step down through a sequence. Okay, so that's a summary, quick summary of what we did during week 1. Okay, so in the first part of our week 2 lectures, we're going to take a look at slices of lists, object ID that you can use to tell whether two different variables refer to the same object, and we're also going to introduce the idea of decisions using if-else, which in turn will require us to talk about the relational and logical operators that Python provides. So a list is an example of a sequence of values. A stir and a range are also examples of sequences. If I create for myself a list called ages, containing some ages of people in a family, let's say. All right, so I've got ages is a list of 5 items, and I can use this notation ages sub and give 2 indices separated by a colon. Now the first index, I here, will be the first item included in this slice from the ages list. And if I use the index 0, that means that I want the 3, the first age in the ages list, to be included as part of my slice. Then I specify a colon, and the second index that I give is actually the index that is one beyond the end of the slice that I want to create. So I've specified 3 here as my second index. What that means is that I want to get all of the ages from ages sub 0 up to but not including ages sub 3. So ages sub 3 is actually the 33 here. Consequently, my slice of the ages list here is going to be just the 3, 12, and 5. If I say ages sub 3 colon 5, well, 5 is the index 1 past the end of the list, but I'm saying here I want ages sub 3 up to but not including 5. That's going to give me ages sub 3 and 4. And so this slice is just the last 2 items from the ages list. If I leave out the first index and just use a colon 3 in this case, 0 is implied. Consequently, ages sub colon 3 is the same as ages sub 0 colon 3, and that also gives me the first 3 items from the ages list. Likewise, a missing J, a missing second index, implies that that second index should be considered as the length of the sequence. Therefore, if I say ages sub 3 colon, that's the same as if I had said ages sub 3 colon length of ages. Well, length of ages is 5, so it's the same as if I had said ages sub 3 colon 5. Okay, so here on slide 4, I'm using the plus symbol to do concatenations of list slices and of string slices. So let's have a look at these examples here. First of all, I'm going to create another list called A with some more values in it. 0, 2, 4, 6 and 1, 3, 5, 7. All right, so A sub 4 colon is going to be the slice of A from item sub 4, well, item sub 4 is the 1, to the end of the list. So that's going to be 1, 3, 5, 7. A sub 1 colon 4 is going to be the slice starting from the 2 and up to but not including the 1. If I say B gets A sub 4 colon concatenated with A sub 1 colon 4, then I'm going to have B referring to 1, 3, 5, 7 followed by 2, 4, 6. All right, and that's an entirely independent list from A, so A has not changed at all here. B is a new list consisting of the concatenation of a couple of slices of A. Now, a string is also a sequence and therefore can be sliced. If I say hello sub colon 3, that means the same thing as hello sub 0 colon 3. That means I'm going to get the sub0, sub1, and sub2 items from hello, which is just the HEL part. And if I then append with plus another string, P exclamation mark, what I get is help exclamation mark as my result. Next, I'm defining S1 to refer to the string international. And I'm requesting 3 slices from international in order to create the string alternate. Now, all of my examples so far have used non-negative subscripts, but if I say S1 sub -2 colon, remember that -2 is the index of the second to last item in a sequence. Actually, I just noticed I misspelled this, so this should be S1 sub -2 colon. Well, -2 is therefore going to be the index of the A, and so S1 sub -2 colon is just going to be the string AL. S1 sub 2 colon 8 is going to be from the sub 2 item, the T, up to but not including the sub 8 item, which is the I. So that's turn at. And then finally, in order to get a string containing an E, I can request a slice from sub 3 up to but not including sub 4. So S1 sub 3 up to but not including sub 4 is just the E character. And so if I append these guys together, let me just hammer that in. The result of this concatenation is the string alternate. Okay, so a list is a sequence, a string is a sequence, a range is actually also a sequence, and range 10, that actually creates something called a range object. The initial value from the range would be 0, and the range is going to go up to but not including 10. If I ask for range 10 sub 5 colon, I get the slice from item sub 5, whose value is actually 5, up to but not including 10. Okay, so that comes back to me as a range function with a narrower range. If I were to say for I in range 10, print I with end equal to space, I'll get the values 0 through 9. On the other hand, if I say for I in just that slice, range 10 from 5 to the end, print I and a space, I just get 5, 6, 7, 8, 9. Okay, so slicing sequences is a very useful thing to know how to do. For example, you'll often get some data from some kind of input file where the lines in the data have parts that you do want and other parts that you don't want. You can use slices within those lines to get the parts that you do want and ignore the parts that you don't want. Okay, it turns out that almost anything in Python is considered as an object. That is, an int value is an object, a float value is an object, a bool value is an object, a stir, the special value none, and for that matter, any list that you create is an object. Range is an object, and many things we haven't talked about yet, like tuples, sets, dictionaries, function definitions, classes. All of these things are objects. They all occupy space in memory, and they all have something called an object ID associated with them. you can use the function ID to find out the ID of any object. Now, I happen to have a string S1 sitting around, and I can use ID to get the ID number of the string. That number in and of itself is not necessarily very meaningful, but it is different from the ID number of any other object. So if I ask for the ID of the integer value 123, let's say, I get some different number. Okay, so in Python, not only do variables and function names and class names have IDs, but even literal values have IDs. So the ID of hello here is this number. The ID of 7 on my system is this number. Now, if I set up a variable x to refer to 7, and I ask for the ID of that variable, I'm going to get the same ID number because the variable is referring to the value, and the value is the object. Okay, x itself is not an object. X is just the name for some object. If I say y gets 7, that implies that y is referring to the same object as x, and so the ID of y is also that same number. It turns out, in fact, that small integer values, it turns out that this means roughly values between plus and minus 256, are pre-allocated as soon as Python starts running, and always have fixed locations in memory, and therefore always have fixed ID numbers. So if I say something like z gets 3 plus 4, z, of course, is now referring to the value 7, and the ID of z is therefore the same as the ID of 7, the ID of x, the ID of y. X, y, and z are all now referring to the same small integer value 7. If I define a list, by using square brackets and a sequence of values, a list is always allocated at some new place in memory. And so here the ID for m is whatever it is, this number. If I define a separate list that happens to have the same values in it, this is not going to have the same ID number. Even though at this moment m refers to a list containing 1, 2, 3, and likewise n refers to a list containing 1, 2, 3, they are different lists. So if I say, for example, m.append 9, that changes what the list m contains. It has no effect on what the list n contains. The ID of m is still what it was when I first asked for the ID of m, and the ID of n is still what it was. Now, if I do something like n gets m, of course, n gets m, this actually changes the variable n to refer to the same list as the variable m. And in fact, what's happened here is I've lost track of this list 1, 2, 3 that n originally was referring to. And in fact, that memory is reclaimed for use by some other object. So now the ID of n is the same as the ID of m. If I display n, I see the 1, 2, 3, 9. If I say n dot delete 2, n dot remove 2, now n has had the 2 removed from it, and of course, since m is referring to the same list, I'll see the same thing reflected through m. Okay, so every object has an ID. There isn't really much that you can do with IDs of objects other than to tell whether two different variables are referring to the same object or not. Now, one comparison operator in Python is the double equal symbol, which I like to pronounce as the is equal in value to operator, or just is equal to operator. If I say m gets 1, 2, 3, this creates a new list containing 1, 2, 3 and modifies m to refer to that list. The ID of m will now be some value other than what it used to be. Okay, so m is now referring to this newly created list 1, 2, 3. And if I say n gets 1, 2, 3, that is a newly created list 1, 2, 3 that n has been modified to refer to. If I ask whether m is equal to n, this is doing a value comparison of one list to another. And it is true that m is equal to n. However, since they are separate lists, if I ask whether m is n, all right, the is comparison is checking whether the two objects are the same, literally the same object. That is, whether the two ID numbers match. So when I say m is n, I get false. This is a fairly typical situation where you have two objects that are equal to each other in terms of their content, but that are not literally the same as each other in terms of being the same object. We can use the result of a comparison, such as an is equal to test or an is the same object as test, in an if decision. An if decision has to have an if part, and the if part looks like if followed by some Boolean expression, let's say n, m equal to n, and a colon. Okay, so that's how you have to start every if decision, is you say the keyword if, then you have some Boolean expression. In this case, I'm comparing whether the value of the object that m refers to is equal to the value of the object that n refers to, and the statement within the if that says what to do if that comparison is true has to be indented. All right? Lucky for me, the shell is smart enough to do the indentation for me, so if I'm using this particular idle shell, I can just go ahead and keep typing. I'm just going to say print m is equal to n. There's the body of my if decision. And if I hit the enter key again, the shell will recognize that I'm done typing this if decision. And because m is equal to n, I will get this print function executed. All right, so I'm told that 1, 2, 3 is equal to 1, 2, 3. Here we have another example. I have a variable a referring to 12, a variable b referring to 12, and I'm saying if a is equal to b, then let's multiply b times 2. Now, because when I arrive at this if decision, the value of a is, well, I should be really careful here. The value that a refers to is equal to the value that b refers to. That test will be true, and I will end up multiplying b by 2, so that when this decision's over, a is still 12, but b now refers to 24 instead. You can go ahead and create variables inside of if decisions. The body of an if decision can be arbitrarily long. Notice, though, that the indentation level has to be exactly the same. So here I'm saying a gets 12 again, b gets 12 again. If a is equal to b, I'm creating a new variable c equaling -4. And then I'm saying b gets a plus c. So b is going to be set equal to 8 here. All right, so b now refers to 8. C exists and refers to -4. A still exists and is unchanged. If I make any mistake as far as indentation, Python is going to scream at me. So if I say if A is equal to B, C equals -4, and then here I accidentally hit a space character, B equals A plus C, Python yells at me here and tells me that I have an unexpected indent. This is frankly very annoying, but it's something that you just have to learn to live with. In fact, even if you just accidentally hit a space bar at the beginning of your shell command here, so my command here is going to be create a variable D referring to 12, even here, Python hollers at me. So Python is very, very picky about indentation. You have to make sure that all your indentation is at the same level of all the other code that's supposed to be at the same logical level of behavior. So what about this indentation business? Well, in some ways it's good because unlike many other languages like Java or C++ or C# or what have you, the enforced indentation rules means that pretty much every Python programmer's code looks like pretty much every other Python programmer's code. On the other hand, something that's not so great about this enforced indentation scheme is that you do have to use line continuation, the backslash at the end of the line, or parentheses around multiple lines, or square brackets around multiple lines, which is kind of nasty. Also, if you have really long code, for example, here I have an if statement that has 2 statements within the body. What if I had an if statement that had 30 statements within the body? Then, because the only thing that's controlling what is in the if and what is outside the if is the indentation level, it's very difficult to see all of those 30 lines on the screen at the same time. It's difficult to be able to tell where your if starts and where your if ends. Whereas in a language that uses something like curly braces to enclose the body of the if, it's relatively easy to spot where the ending curly brace is, even if the opening curly brace is up off the top of your screen someplace. So indentation is simply a fact of life in Python, and it's up to you, I guess, to decide whether you want to complain about it or not, but there you go, you have to live with it. Optionally, but very commonly, an if decision will have an else part, so that if some expression is true, one thing happens, else or otherwise, something else happens. Here's the general syntax of that here on slide 15. Let's take a look at a particular example. And rather than type this thing in manually to the shell, which is error prone, it's going to be highly unlikely I can do this without making stupid typing mistakes. I type this into an editor. Let me pull up that editor screen. So here's the same thing in a file named ifelse.py. We're saying x gets 12.3, then if x is less than 12, print that whatever the value of x is less than 12, else or otherwise print x is not less than 12. And when I run this module by pressing F5, it will execute in the shell, and I get told 12.3 is not less than 12. Okay, so no big surprise there. Furthermore, in addition to the required if part and the final optional else part, you may also have elif parts in between. And you can have any number of these elif parts, including 0. Elif is simply an abbreviation of else if, of course. And the idea is if the first Boolean test succeeds, then we're going to perform the body of code in the if part. Else if some other Boolean test succeeds, is true that is, we'll perform that section of statements. And this can continue. Else, if something else is true, do something else. Else, if still another thing is true, do still another thing. And then finally we can have one else at most at the bottom. Here again, Let's look at a specific example. And again, I have typed this into an editor. Okay, so here is this code in an editor. We're saying x gets 12.0. Now, importantly, x is referring to a float in this case rather than an int. I'm testing whether x is less than 12 or, all right, or is a logical operator that allows me to ask whether something on its left is true or something on its right is true, or x is greater than or equal to 13 in this case. So if either x is less than 12 or x is greater than or equal to 13, we're going to execute this print function call. Well, of course, 12.0, the value of x, is not less than 12, nor is it greater than or equal to 13. Therefore, the test in the if is going to be false. And we're going to next come down to the elif part. Now here we're asking if x is 12. And you might look at this and think, well, 12.0, 12, same thing. Actually, no. 12.0 is stored as a float object. 12 is stored as an int object. And a float cannot be the same object as an int. So here again, x is 12 is going to fail. That's going to be false. So we will eventually drop down to the else part and display the value of x is whatever it is, in this case 12.0. Let's execute this. And yes, we get told the value of x is 12.0. Here is the complete collection of equality and inequality operators, relational operators, identity comparison operators, and logical operators, logical not, and or. This table shows the precedence of these things from highest precedence to lowest precedence. If you are familiar with some other C language relatives, such as C++, Java, C#, this precedence hierarchy is going to cause you some problems, probably. The double equal to is the is equal to test. Exclamation mark equal is the is not equal to test. And in other C language derived languages, those actually have lower precedence than the relational operators do. Having them all at the same precedence can cause you some confusion. Furthermore, in other C language related languages, not actually has the highest precedence, although in those languages it's simply an exclamation mark rather than the word not. Having not at a lower level of precedence is likely to cause you some headaches. And has lower precedence than not, or has the lowest precedence of all. You can use parentheses either for overriding these precedence rules or for just clarifying complex comparison logical expressions. Okay, so that is it for week 2, part 1.